on the way in. There's still plenty on the table over there. Get them on the way out. Our talk tonight, A Trip Through the Light Fantastic, by Frank Summers of Space Telescope, and I'll introduce him in just a minute. Let's say upcoming, our talks. As I said, I'm trying to get somebody from New Horizons to do the October talk, but I haven't had much success. I was on vacation a lot this month, so I am a little bit behind on things. November, we have Mario Livio, and I looked in my email today, and he still hadn't given me a talk title, so I have to contact him tomorrow and say, Mario, give me a talk for November. And in December, Lucy McFadden from Goddard Space Flight Center, one of the lead people on the Dawn mission that went past Vesta a couple years ago and went to Ceres, is currently orbiting Ceres. We'll give a talk on Dawn, A Journey to the Early Solar System in December. I'm extremely excited to have Lucy come up here in December. If you want the latest information, you can go to our website. You can do hubblesite.org go talks, or if you just put Hubble Public Lecture in your favorite search engine, this should be the page that you get, which lists our upcoming lectures. And it also has a link to our wonderful STSCI webcasting team archive. Our webcasting team has the archive of them all the way back to 2005. You've got 10 years of public lecture goodness to explore. So if you've got a free weekend or a free few weeks, you can watch them all back to 2005. All right, if you would like announcements, you sign up. This is new because we started this in the spring, maillist.stsci.edu, okay? And you look for public lecture announce. I think there's only one or two mail lists that are public on that. Anyways, just provide your email address and you will not be getting any spam. Or if you would like to have us sign you up for it, you can contact us at publiclecture@stsci.edu. You can sign up for the announcements, or if you have comments or questions you would like to ask, please send them to that email address. We have social media for those who do it. Of course, we have Facebook, we have 2 different Twitter feeds, we have Google+, we have Pinterest for those who do that. I think we probably even have, what's the other one? Instagram. I don't know if we have that. I'm sorry, I only do so much. I do Facebook and Google+ and Twitter for my stuff. Unfortunately, not as much as I should. I just have so much stuff to do. It's hard to keep up doing a lot of social media, but I will try and keep up. All right? The observatory tonight, the weather is permitting. I got an email saying, yes, the observatory is on. So after the lecture, if you would like to go across the street to the Maryland Space Grant Observatory, which looks something like this up on the Physics and Astronomy building across the street. The person, I believe it's Duncan. Is it Duncan? He's not here right now, obviously. We'll be here afterwards. Come down, meet here as a group, and walk over across the street as a group. You cannot go over on your own. You have to go over with the group because he's got to let folks in certain doors, etc. Okay? All right. Normally, I would be doing news from the universe for September 2015, but as is my tradition, whenever I give the talk, I don't have enough time to prepare a news summary. It takes a little while to do that. So, as I promised, I will make sure you get your full dose of Pluto next month, okay? All right, we get lots of Pluto next month. Now, I get to introduce our featured speaker. And when I give the talk, all right, how many people are new here? Haven't been here before? Wow, we got about a dozen. All right, so let me do my introduction. The rest of you can close your eyes for a second. I'm an astronomer in the Office of Public Outreach here. I've been here for 14 years. I work on all things Hubble, whether they be press releases or websites or educational activities or working with planetaria. My favorite things to do are astronomy visualizations. All right, and so I've got a history doing, and I am an astronomer, but actually I'm a professional outreach astronomer. I have been doing outreach only for over a decade. I've been about 2 decades worth of outreach astronomy. So I don't do research anymore. Now, for the rest of you, when I do these talks, since some of you have been here longer than I have coming to the public lecture series, I like to show you something that you may not remember about me. So, our featured speaker tonight, when he was young, This is a picture of the astrophysicist as a young man. This is me in 1983, was it? This is the Paso Doble costume. I was a competitive ice dancer. This photograph by David Leonardi, the photographer of all the great ice skating stars. And my skating partner, Sandra Lynn McGee. I was a competitive ice dancer for, I don't know, about a decade or so. And I retired at the ripe old age of 20 or so. I was ranked 10th in the United States when I retired. So I like to show pictures like this to say, hey, you know what? You can be an astrophysicist geek, but you can also have an artistic background. Okay, and so I was a competitive ice dancer before I became an astrophysicist. The two are not mutually exclusive. We have at least one example of that. All right, so let us switch windows and go to tonight's talk. All right, so tonight's talk is a trip through the light fantastic. And as I said in my previous intro before this is a talk that I have given to educators. I've spiced it up a bit and changed it around just a little bit in terms to present it for the public. But it is really, it's a fundamental idea of the electromagnetic spectrum. And the electromagnetic spectrum that underlies astronomy, but also underlies lots of other sciences because it is used in physics, it is used in underlying chemistry and in biology, understanding the idea of light. And when you think about astronomy, you might have that romantic notion, that idea of the astronomer standing at the telescope, looking through his giant telescope, perhaps up on top of a mountaintop. And that's just not how it is anymore. That's how it was 150 years ago when this engraving was done. This is from 1848. This is the telescope at the Cincinnati Observatory, which at the time was the second largest in the country. Cincinnati, second largest telescope in the country at that time. But what do astronomers look like these days? Do they go up to the mountaintops? Yes. But what do? They sit in front of banks of computers, okay? They don't put their eye up to the telescope. It's not that poetic anymore. We have CCD detectors that do all that for them. Everything becomes digital. It comes to the computers. And you sit there at the keyboard with your notes and everything and very carefully taking advantage of it. Also, astronomers have used other wavelengths now. All right? We do radio observations, okay? Giant radio dishes. And where are you going to put your eye on this? Are you actually going to go there? Well, actually, you know, the Jodie Foster character from the movie Contact notwithstanding, and that the idea was that she was actually listening to the radio signals that were being detected by these dishes. Yeah, it doesn't happen, okay? Nice poetic idea for the movie. Yeah, doesn't happen. So when we are looking in wavelengths that our eye can't see, of course, we have to be doing detecting. You have to be using detectors to do this. And one of the great advances of 20th century astronomy was 100 years ago, all we were doing was looking with our eyes, okay? And we started to take photography in the late 1800s, but we were using visible light astronomy until we started to exploit the other wavelengths. Radio waves came first, but we now do astronomy across the entire electromagnetic spectrum. And so what this trip through the light fantastic is about, is to show you the variety of ways that we look at the universe and remind you of the different things that we can see using the different types of light. So let's begin with visible light. Visible light is, of course, the light that the human eye sees, right? And it is also the light that is given off most by our sun. This, of course, is not a coincidence. If you want to see in the light of the sun, well, it helps if your detector is tuned to the wavelengths given off by that sun. Here are four black-body curves of various stars. So our sun is approximately a 6,000 degree Kelvin star, so it's this curve in here in the middle. And the upper curve at 7,000 degrees Kelvin is a hotter star. The 5,000 degree Kelvin is just a little cooler than the sun. And then the 3,000 degree Kelvin is a red dwarf, much cooler than the sun. All right, and so this is the emission, all right, the amount of emission on the y-axis by wavelength on the x-axis for various stars. And where does the sun peak? Right here in the visible wavelengths. All right, the hotter stars can move toward the ultraviolet. The cooler stars actually have their peaks out in the infrared. So visible light is where our sun emits most of its light. And if you know anything about our sun, you know that we call it a yellow star. However, this is wrong. Okay? Our sun may be called a yellow star, but it is not a yellow star. We do not see a yellow star. You have been lied to your entire life because they draw a blue sky with a yellow sun in it, okay? That's not what the sun looks like. If you look at the sun and you measure its color as perceived by the human eye, you take that black body curve, you map it through the RGB cones of your eye, the color you will get is something like this. Our sun is mostly white, okay? It may be called a yellow star, but emits white light. Actually, you know, if you do it really carefully, I see a little bit of peach in it, okay? It's mostly white, but a little bit of peach. Now, this color comes from my monitor to the projector to the screen, etc. So there's no real color fidelity here. I can't show you exact color matching here. But basically, the sun is mostly white, okay? Now, of course, white light itself can be broken down into all the colors of the rainbow, okay? That red, orange, yellow, green, blue, violet of that rainbow is really just breaking up the sun's light into its component wavelengths to see those various colors. All right, so sun emits white light. White light is actually composed of many different colors. Now, we see a lot of things in astronomy using visible light. So we look at the moon, and here's a gorgeous picture of the full moon out over the ocean. But the moon doesn't emit light, okay? The moon only reflects the light of the sun, okay? It's important to recognize that the sun emits the light, but the moon only sees by reflected light. Jupiter also, in visible light, we don't actually see it. It does not emit visible light, but it reflects the light of the sun. Jupiter, as I'll show you a little bit later, actually does emit some infrared light. It actually is glowing in infrared, but it is not glowing in visible light. It is just reflecting the light of the sun. Asteroids, they're not glowing. They're just reflecting the light of the sun. What about comets? Comets are really cool. They look like they're actually glowing, like they're actually emitting light, but again, they're also just reflecting light. Okay, so most of the things we see in the solar system are just reflecting the light of the sun. The sun is our source of visible light. If we look at other stars, are they emitting light? Yes, of course. Right? But I like to show the Pleiades because all this blue gas around here, it's called a reflection nebula. That gas is not glowing because it's hot. It's glowing because it's reflecting the light of the stars around it. The Pleiades are a relatively young star cluster. The gas from which they were formed hasn't fully dissipated away, and so you're seeing some of the gas around them reflecting the light of the stars. If instead you go to the Orion Nebula, well, the hot stars at the core of the Orion Nebula have heated this gas, so the gas in this nebula is glowing. It's heated up to a high enough temperature that the gas itself is glowing. All right, and so it's important to recognize as an astronomer when something is actually glowing in that light and when it is just reflecting the light around it. We have to analyze the situation. And for things like a supernova remnant, this is the Crab supernova. The interior of this was actually heated to millions of degrees. This is a visible light image of specific wavelengths detecting specific elements in the external parts of the supernova remnant. This, of course, is also gas that is glowing. There's also gas that is absorbing, that is easily seen in this image of the Whirlpool galaxy. So we have these pink regions, which are the star-forming regions. We have the blue stars and the yellow stars on in here. But we also see this marbling, this dark stuff here. Well, that's gas that's not emitting light, that is absorbing the light. It's blocking the light. So we have bright nebula, we have reflection nebula, we have emission nebula, we also have dark nebula that we can't see that's actually blocking the light of other stars. So when we consider visible light, our base thing, how do we remember it? Well, probably in school you learned something like Roy G. Biv. Now, how many of you actually had indigo in there, B-I-V, right? Raise your hands. Yes, the older kids, even the younger ones. Oh, okay, your textbooks haven't been updated lately, have they? I don't know when indigo was removed from this, but it was many decades ago, I thought. A lot of the people learned Roy G. B-I-V. The indigo is no longer used, so it's just red, orange, yellow, green, blue, and violet for the colors of the spectrum of visible light. And the important point about this is recognizing that these are all the same phenomenon of light, but they have one characteristic different. And you can consider that characteristic of energy, that red is lower energy than violet, or frequency, or wavelength, okay? And wavelength actually increases the opposite direction of frequency. Now, on this next slide, I'm going to get into an equation. This is something that I definitely do for the teachers, but since some teachers will probably watch this in the archive, I want to put it up there, okay? So, for the fundamental equations, all right, the fundamental properties of light to understand is that it's a wave, okay? All right, and the energy of the wave is proportional to the frequency. The higher the frequency, the more energy. You can have a slow frequency, you're low energy, all right? And then you get up, that's higher energy. Makes sense, right? And the proportionality constant is called Planck's constant. That's what this little h is here. This v is traditionally a Greek letter nu for the oscillations per second measured in hertz, okay? And then the other thing to recognize is the other equation that we need to know for light is that frequency times wavelength is equal to the speed of light, okay? They're inversely proportional to one another. So you've got this frequency, which is nu. The wavelength is represented by lambda. Together they combine to make the speed of light, and this is constant throughout it, okay? So that as frequency goes up, wavelength has to go down. As wavelength goes up, frequency has to go down. They're inversely proportional to one another. All right, so if you want to make a real geek joke, somebody says, hey, what's new? You say, C over lambda. It takes a while for that one to sink in, yes. Okay, so that's your physics joke for the night. There are actually a few more jokes here, but we'll leave that alone. So when we think about this visible spectrum, we're now taking an increasing wavelength here, okay? So the longer wavelengths are over here. All right, so we reversed it from the Roy G. Biv. All right, but the visible spectrum is only a tiny part of the entire electromagnetic spectrum, okay? So those are the different properties of visible light, but they're also the same properties of the entire electromagnetic spectrum, which includes gamma rays, X-rays, ultraviolet, infrared, microwave, and radio waves. The whole point is that all of these are the exact same phenomenon, just having different wavelengths or different frequencies or different energies, okay? So when we think of the electromagnetic spectrum, we don't think that X-rays are something totally crazy different from the normal visible light, or that radio waves are something, you know, unfathomable compared to visible light. They're all the same thing. But these have shorter wavelength, higher frequency, and larger energy. These have longer wavelength, lower frequency, and smaller energies. That's the point of the electromagnetic spectrum. So let's take a trip across this electromagnetic spectrum and see what we see. We're going to start with the low energy and the long wavelengths. Radio waves, okay? Wavelengths, roughly, and I got to say these divisions aren't set in stone. Here are some rough divisions. The wavelength is longer than a meter, okay? So this is a wave about that long, okay? And longer, and longer. This is why we need giant radio dishes, okay? The frequency is low frequency, less than 300 million hertz. Yeah, 300 million hertz is low frequency, folks, okay? When we get up to other things, it'll get unfathomable, and actually I'll stop using frequencies. So when we think of radio in our everyday life, well, we think of a radio. This is actually a multi-band radio that has not only your familiar AM and FM channels, but also a bunch of shortwave and other wave channels across here. If we look at the AM and FM that you're used to, AM stands for amplitude modulation, and that's 540 to 1600 kilohertz. Okay, kilo meaning 1,000. So the most listened to AM radio station in the country is WABC AM 770. That's 770 kilohertz or 770,000 hertz. So the oscillations are going 770,000 times a second in order for you to listen to that radio station. That's a lot of frequencies, okay? That's a lot of up and down. FM radio, which uses frequency modulation to send its signal of the sound, is 88 to 108 megahertz, all right? And again, this is a New York City radio station. We have another New York City radio station that's #1 in the rankings for FM, WPLJ 95.5 megahertz, which is 95.5 million hertz. All right, so these are the frequencies that you're used to. You're working with them all the time whenever you turn your radio dial. You're getting either hundreds of thousands or millions of cycles a second when you turn on that radio dial. Astronomers, when we turn on that radio dial, well, I showed you one giant radio dish. We can also tune it even larger. This is the Very Large Array in Socorro, New Mexico, which has a whole bunch of these dishes, all right, arranged out in a Y formation. So we can set them apart to synthesize a telescope that's even larger. As I said, radio waves, we're talking a meter or larger. This, we're talking things that can be set across distances of miles. And actually, astronomy uses something called very large baseline interferometry, where we have astronomy radio dishes across the globe acting as a single telescope to try and do really, really large baseline astronomy. Okay, so radio waves can get up as far as you can set a standard base for them. What do we see? Well, here is a picture of Jupiter in visible light. Okay, now Jupiter has a very large magnetic field. It's actually it's actually the size of its magnetic field is larger than our entire sun in terms of it. But inside that magnetic field, there are electrons bouncing up and down those magnetic field lines. All right? And when we look in radio waves, Jupiter looks like this, where you can see those magnetic field lines, all right, and what we call the decametric radio wavelengths of the electrons bouncing up and down inside those magnetic field lines. So the magnetic field of Jupiter emits a lot in radio. The Whirlpool galaxy, the galaxy that I showed you before, all right? This is what it looks like in visible light. I'm going to shrink it down to this size. This is a Hubble image with visible light, and I'm going to show you what we see in radio waves. In radio waves, you can see this, in visible light, you can see these beautiful spiral pattern, but in radio waves, we can see the gas that extends off of it. All right? You can see that there's a lot more gas stretching out here. This is the neutral hydrogen gas. That you can see that there's evidence here of a lot more dynamicism happening due to what we can see in the radio waves. So what this is actually a composite image with a ground-based visible light composited onto the radio waves. And you can see that there are, in radio, we can detect a lot more gas extending well beyond the visible extent of the Whirlpool galaxy. One other example for radio, we'll talk about a supernova remnant. Okay? So this is the supernova remnant Cassiopeia A, the result of a star that just blew itself apart. Okay? So in visible light, we can see that shell, the shell of material of a star that blew itself apart. In radio waves, we can see a lot more complex structure. All right? Because visible light gets things that are at thousands of degrees or tens of thousands of degrees. If you are heated up to thousands or tens of thousands of degrees, you are hot enough and you radiate invisible light. Radio waves will take the lower energy stuff and see a lot more structure throughout the surrounding thing of that supernova remnant. Oh, what I forgot that I had one more of these. The other thing that's fun to do is to take a visible light image and compare it to a radio image. Now, here is a composite image from Hubble and the Very Large Array. So what we've got here is we've got a galaxy, a giant elliptical galaxy. At the core of that giant elliptical galaxy, there's a supermassive black hole. And that supermassive black hole is spewing out high energy radiation. Okay? Around that supermassive black hole, there are oppositely directed jets spewing out from that supermassive black hole. And that, although that supermassive black hole is on the scale of a solar system, those jets of radiation extend not only across the solar system scale, not only across stellar scales, but across the entire galaxy and outside the galaxy, as seen in this radio image. So there is something in here that's on order of a solar system scale, spewing out jets that extend 5 times further than the visible extent of this galaxy. So if you want to see the power of a supermassive black hole, you don't use visible light, you go to radio, where you see these radio galaxies and these giant radio lobes spewed out from the supermassive black holes at the core of these galaxies. Kind of cool. All right, radio wavelengths get us all sorts of fun stuff, but that's not the only place we're going to go. We're going to go to microwaves. Now, radio waves were longer than a meter. For microwaves, we're going to go from a meter down to about a millimeter. Okay, so that's about a factor of 1,000 in scale for millimeter. And here we're getting frequency, again a factor of 1,000 in frequency, from 300 million hertz to 300 gigahertz. All right, you might have heard the phrase gigahertz used in some things. In particular, you might have heard it related to, what do we think of microwaves, right? We think of microwave ovens, all right? And microwave ovens heat your food by basically heating the water. All right, it's dielectric heating. It causes basically the water molecules to spin, because water molecules are not symmetric in terms of their electric charge. They're electrically neutral, but it's not symmetry. And you can get those water molecules to spin by either exciting them with a 2.5 gigahertz or a 12 centimeter. What's about 12 centimeters? That's about 12 centimeter, a 12 centimeter wavelength, or a 915 megahertz, which is about a 32 centimeter wavelength. Okay? Using that, you can excite the water molecules in your food, which causes them to heat up. All right? So microwave ovens do use microwaves to heat your food. Astronomers, when we want to look at microwaves, well, we use something similar to what we use for radio, but they can be smaller dishes. This is the Atacama Large Millimeter Array, or otherwise known as ALMA. It's on the Atacama Plateau in Chile, which is up at like 15,000 feet. All right, and it's incredibly dry, and this is a place where you actually you can't breathe very well. Okay, I like to make the joke that astronomers now need Sherpas in order to do astronomy, because the astronomers, can't think very well. The astronomers, when they go to this telescope, they don't go to this telescope. They go down the mountain, and they're about 9,000 feet. Okay, the same is true on Mauna Kea. When you go to that telescope, you're at 9,000 feet. The telescopes are much, much higher above you, but only the workers who train and can use this are working up there. The astronomers all stay down, so you really don't go to the telescopes when they're this high. But ALMA has produced and will be producing some amazing images. I'm going to show you one of its most amazing coming forward. So let's return to that whirlpool galaxy and take a look in millimeter wavelengths. Okay? So when we look in millimeter wavelengths, you can see all that dark gas in here. All right? That gas is dark with visible light. In millimeter wavelengths, it shows up really strongly. What we're seeing in here is the really dense cold gas, that very densest, coldest gas along those spiral arms. These are the densest cloud regions along inside this galaxy. So if I go back here, you can see the densest regions, all right, the densest regions of invisible light, all right, show up as the brightest regions in millimeter wavelengths. So if we want to study the molecular gas in a galaxy, we go to the millimeter microwave region in order to see the details of what's going on inside. We can also do the same thing for disks around stars. Now, this is a Hubble image of the disk around a star 107146, HD 107146. I always have to read that because I can't memorize these phone numbers. Now, what we've done here is that we blocked out the light of the star in order to see the material in a disk. So this is basically a face-on disk, a thin disk around a forming star. All right? And in that disk is where we expect to see planets form. All right? And so Hubble can see that these disks exist, but it can't see a lot of the details. Microwaves can actually show us a lot more. So this is a star called H.L. Tauri. It is Hubble's view of it, and H.L. Tauri is in here, and it's all shrouded by all sorts of dust. We really can't see much about H.L. Tauri in visible light. But if you go to the ALMA array and you take a picture, you get this image here. This is not an artist's illustration. All right? This looks to me like an artist drew these concentric circles. This is an actual image from the ALMA array looking at a disk around H.L. Tauri. All right? And we can see that there are these wonderful, beautiful concentric gaps in the disk around H.L. Tauri. This is exactly what we expect from planet formation. When you start to form planets, you get gravitational perturbations, and the material flows onto these planets, and they will pull out these gaps inside these disks. Now, we can't say that there's a planet inside every one of these gaps, because, of course, what we get is not only just the gaps where the planets form, but you also get gaps in terms of resonances, gravitational resonances in that same disk. So if you're, if this thing orbits twice for every time this orbits once, you get a resonance there, and you can actually get a gap not where the planet is, but where a resonance for that planet is. So in using the ALMA array, they're able to get this amazing image. This is one of the first images released from ALMA, and shows that there should be some amazing more things coming up. One other thing that I have to go through from microwaves is taking a look at some all-sky photographs. Now, I want to prep you for that by showing you an image of Earth. Okay? We know that Earth is a globe, but when we want to put it onto a map, we generally have to distort it to put it onto a map, right? The Mercator projection is all things, all sorts of distorted. Greenland looks way too huge. So when we try to take a sphere and put it on a flat piece of paper, we use various projections. This is one called an ATOF projection, okay, which takes a sphere and roughly distorts things less, all right? Creates a nice oval out of the sphere and distorts things a little less than other projections, all right? So everything I'm going to show you from here on in is not the Earth, but it's the entire sphere of the sky projected in this ATOF projection, all right? So now I have for you an amazing image, an image worthy of two Nobel Prizes, okay? This next image led to 2 Nobel Prizes. You ready for it? There it is. That's 2 Nobel Prizes worth. Okay, let me explain. This is an image of the cosmic microwave background, okay? As we look out into space, we're also looking back into time, okay? When the universe was really, really young and really, really small and really, really hot, it actually glowed. And the light from what we call the surface of last scattering has free streamed across the universe. It started out at several thousand degrees, but because of the expansion of the universe, it has cooled down to about 3 degrees. All right? And because it's at 3 degrees, that means its emission is now observable in the microwaves. So Penzias and Wilson at Bell Labs found a radio signal in their microwave antenna that they couldn't identify, and it was uniform across the entire sky, which is why this is such a boring image, okay? But this is the remnant radiation of the early universe from about 500,000 years, 400,000 years after the Big Bang. As the universe expanded and cooled, there's a surface at which the last light leaves, and that light comes across the universe, and it's available in every direction, because in every direction we're looking out into space, we're looking back into time, we're seeing the relics of the early universe. And so just getting this discovering this 3-degree Kelvin microwave background radiation was worthy of a Nobel Prize. The second Nobel Prize comes when you look deeper into this image. So let's take that average 3 degrees, it's actually like 2.73 degrees, and we'll subtract it off to see what we get. Okay? So we take rid of the average, and we come and we get a cosmic yin-yang symbol. Well, that's not actually what you're seeing. What you're seeing here is it's a little bit hotter in this direction, a little bit colder in this direction, because the Milky Way galaxy is moving through the universe. Okay? So that actually is, what you're seeing is actually the Doppler shift of the galaxy moving through the universe. So this isn't really any cosmic signal. It's just due to the motion of our galaxy. So let's subtract that off. And what do we see? We see this big red line across here. Well, that actually is the emission from stuff inside our galaxy. That has nothing to do with the cosmos. That's just our galaxy. So we work really, really hard to model the emission of our galaxy in microwaves. And then we subtract that off. And what do we get? We get the result from the COBE satellite. Okay? So you've taken out the average, you've taken out the Doppler motion of the galaxy, you've taken out the emission from the galaxy, and what you are left with is the tiny variations in the cosmic microwave background radiation. All right? So you're seeing the universe as it was 500,000 years after the Big Bang, and now you're seeing that it has tiny little variations. Those tiny little variations are actually density variations. It's a little bit more dense here, a little bit less dense there. You're seeing the seeds of structure formation. These are the tiny, tiny seeds of structure formation that will then grow into galaxies and clusters of galaxies and superclusters of galaxies. And this is so important. It's not just the COBE satellite, but we followed that with the WMAP satellite, and that was followed up with the Planck satellite in order to get more and more detail in the cosmic microwave background. We're studying the seeds of structure formation in the universe in microwaves, and not just just first the initial discovery of it merited a Nobel Prize, but the discovery of the variations in it also merited a Nobel Prize. Seeing the beginnings of structure forming in the universe. That's what we see in microwaves. All right, let's move on to a little bit longer. Infrared light. Okay, so let's see, we've got about 1 millimeter down to about 700 nanometers. So that's a little over a factor of 1,000 for infrared light. Now, when you think about infrared light in your daily life, all right, anybody here computer gamers? Okay, and you play Call of Duty and they have that mode that, you know, where you can see things in the dark, right? Okay, that's called night vision, and a lot of people think that that's infrared vision, all right? And it's not. Night vision, especially as it would be used in Call of Duty or anything, is just enhanced low light vision, okay? So when you see a picture like this, you're amplifying the light around it, okay? It's not infrared light. There is some infrared light that you can use like that. But really, when you want to look at the infrared, you're going to get pictures like this, okay? So this is a visible light image of a firefighter, all right? And the same infrared image of that firefighter shows him glowing, but also shows that human person on the floor glowing. All right? Using infrared light, you're seeing heat radiation. Okay? All right? Where things may be obscured in visible light, the heat radiation can go through. You are all emitting infrared radiation right now. Okay? Objects at room temperature emit infrared radiation. Okay? All right, you're at hundreds of degrees in Kelvin, you are emitting infrared radiation. If you're at thousands of degrees Kelvin, you're emitting visible light. You aren't that hot, I hope not. I sincerely hope you're not that hot. But you are emitting infrared radiation. Now, for astronomers, infrared radiation has a variety of ways that we detect it. Some infrared radiation makes it through our atmosphere to the ground, so we can observe infrared radiation with normal telescopes, okay? So these are the twin Keck telescopes atop Mauna Kea. All right, they're giant light buckets, really, really good for observing in the infrared. However, if you get up above, higher in the atmosphere, the higher in the atmosphere you get, the better your view is. So why not take an infrared telescope and put it on a plane? Okay, this is SOFIA, the Stratospheric Observatory for Infrared Astronomy, and that is the hatch that is open for an infrared telescope. You fly it up at high plane altitudes, you get a better view of the universe. Okay, and of course you can go up into space, you can take it further up into space And you can have the Spitzer Space Telescope, which is an infrared telescope, and the upcoming James Webb Space Telescope that will launch in 2018, also an infrared space observatory. All right, so infrared is able to do from the ground, from airplanes, and from space. Oh, by the way, I will also note that these two are not to scale, okay? The main mirror of Spitzer is smaller than one of these mirrors for James Webb, okay? So this is a 0.8 meter mirror telescope. This is a 6.5 meter telescope. So you can see what an incredible improvement this will be over that for infrared space astronomy. So I told you Jupiter is actually glowing in the infrared. This is a visible light view of Jupiter, and here is an infrared view of Jupiter. All right, and you can see the emission coming from the internal of Jupiter. And in particular, one of my favorite things is that the Great Red Spot, as well as Red Spot Junior, okay, Great Red Spot and Red Spot Junior are sources where infrared light is escaping from the internal on Jupiter. If you look at an infrared, one of my favorite infrared images, you can see how bright it is here in the Great Red Spot, and for Red Spot Junior, in terms of seeing the infrared light coming from them. Really gorgeous infrared view. Infrared is also incredibly useful with not just looking at planets, but in terms of looking at nebulae. This is one of the famous images we released for Servicing Mission 4 in 2009. And here we have the pillar in the Carina Nebula. And you can see that you've got a good number of stars around it, but you can see there's all this gas emission. Well, infrared light has longer wavelengths than visible light, so the wavelengths penetrate through that gas. All right? And so the infrared version of this image from Hubble is this. All right? There's the visible light. There's the infrared. Look at all the stars you see because you are peering through some of that gas. Furthermore, if you go in detail, there is a star forming in here. Okay? There is a star forming inside there that is not clearly visible in visible light. Yeah, visible in visible light. Recognizable in optical light. How about that? Change that. But if we go to the infrared, there you see it right there. Okay? There's a star. You can see the jet of emission from that newborn star. We go back. You can see that there's a little bit of something here that you can see with visible light, but there you can see the star. So if you want to study star formation, right, you want to go to the infrared. This is one of the main tasks of the James Webb Space Telescope, will be to look at places where stars are forming, to peer into that dense gas and see deeper in to see the structure of star formation in the infrared. Let's go back to the Whirlpool galaxy. This is not that Hubble image of it, because we're going to compare it to a Spitzer image. This is a ground-based image from the National Optical Astronomy Observatory. And here you can see that beautiful pattern of the whirlpool. Again, let's highlight those dark dust lanes, because in the infrared, those dust lanes are glowing. All right, there's the visible light. There's the infrared. All right, if you look right along here, you can see visible light, infrared. All right, those gas, instead of being dominated by the stars and the bright stars in the galaxy, you are now this view is dominated by the cool gas in the galaxy, the warm gas in the galaxy, not the very cold gas, the dense gas that we saw in microwaves, all right, millimeter observations, but instead this is slightly warmer than that. For that, again, infrared is generally hundreds of degrees temperature in the gas. So we can see different phases of the gas by looking in different wavelengths of light. Okay, so now we've gone halfway through and we've got up to visible light. And what I want to notice about visible light, because I've already talked about visible light observations, is that it only goes from 400 to 700 nanometers. That's less than a factor of 2. We're talking about factors of 1,000 for these wavelength regions. All right? When we look at the electromagnetic spectrum, just drawing in all these colors overstates the size of visible light in that. It's not that important a region. The only reason that visible light is important is because it happens to be the region with which we see. It's a tiny, tiny region within the electromagnetic spectrum, because most of the other regions are much, much larger than that in terms of the size of wavelengths that they cover. All right, but since it's ours, we'll keep it as a real spectrum. But you know, it's not really a respectable one. Okay, you know, we've kicked Pluto out as a planet. Maybe we should kick visible light out as a band of the wavelengths, right? You know, it just should be a subset of infrared or a subset of ultraviolet, right? Maybe. Yeah. All right. All right, let's move on. Ultraviolet light from 10 nanometers to 400 nanometers. You can see that's a factor of 40, okay? So a factor of 2 for visible light. That's my point. All right. When we think of ultraviolet light in our everyday, we start thinking about going to the beach and going out in the sun and getting a tan and everything, okay? And of course, when we think about ultraviolet, we talk about ultraviolet protection and what's the UV blockage of your sunglasses, and does your broad spectrum sunscreen protect you against the ultraviolet rays? Well, I happen to have kind of, you know, sensitive skin, okay? I need to use lots and lots of sunblock, okay? But I'm really, really glad that we have an atmosphere, because our atmosphere actually absorbs most of the ultraviolet radiation, okay? We cannot do ultraviolet astronomy from the ground, all right? You can see by this diagram, here is the penetration depth of the various wavelengths. You can see we have the optical window, we have the radio window. You can see how infrared some gets to the ground, some can go there, but we really still need to do infrared. To do infrared right, you got to go to space. Well, for ultraviolet and longer, you got to go to space to do astronomy. All right, which also means that if we didn't have that atmosphere there, it would be really, really bad, because we'd get some serious, serious sunburns. Okay. When we go up into space, we have one of the telescopes up there is the GALEX, the Galaxy Evolution Explorer. It's a telescope that seems to have only one press release drawing of it. I was looking around saying, oh, this is kind of, overdone a little bit with the sun peeking over there. I was trying to find another GALEX. That's it. That's all I could find on the internet today for GALEX in terms of being a thing. But this is an ultraviolet telescope. And as you may know, the Hubble Space Telescope observes a little bit of the ultraviolet. So you can use normal optics to observe ultraviolet. And so this is, of course, tuned with the ultraviolet detectors to see in the ultraviolet with GALEX. So what is our favorite targets, astronomical targets in the ultraviolet? One of them is our sun. Now, our sun in visible light looks kind of boring, okay? It's just kind of smooth and it has a few freckles, right? You put that, you observe it in ultraviolet, and then you start to see the energy in the sun. So these are 4 different wavelength bands, 4 different observation regions within the ultraviolet. Okay? And one of the great things these solar astronomers have done, they've decided that for the various wavelengths, they're going to use single colors. So whenever you see this red, you can know that it's 30.4 nanometers, or 304 angstroms, okay? I think this blue is 19.1. I can't remember all of them. All right, but you can see the structure, and you can also see the magnetic storms that are going on with those sunspots. Those sunspots with visible light, they just look like freckles on the sun. Here you can see the energy that is in the magnetic concentration around those sunspots, the energy that is working through here. And if you ever see anything with, with magnetic storms on the sun and there's exciting images, well, you're looking in the ultraviolet. Matter of fact, ultraviolets, because the ultraviolet images have gotten so popular, you'll see a lot in textbooks that the art director will say, oh, I want to use that image, right? Because it's the ultraviolet. Of course, you have to make sure people mark it as ultraviolet so that if you see the sun looking exciting, you're probably looking at an ultraviolet image of the sun. Another thing that we can see in ultraviolet that we can't see in visible light is the aurorae on Saturn. Now, this is a composite image, okay? These are 3 images of Saturn composited together. They're visible light images of Saturn. Added onto it is ultraviolet images that show off the aurora of Saturn. Now, our aurora on Earth, we can see, how many people here have seen the aurora? Okay? I highly recommend it if you can get north Sometimes you don't have to go too far north to make an effort to see it, because it's really great to just sort of see this shimmering in the sky. I was on a cruise back from Alaska, and we were standing on the back of the boat just watching the aurora dance in the sky. It was really great. So I highly recommend taking the effort, okay? All right, take the effort to go out and see these things, because you live in cities with lights and all that stuff. You don't get to really experience the sky. Make the effort to see it. So see the aurora on Earth, but I can't tell you to go do that on Saturn, because on Saturn, it's not visible light aurora. It's ultraviolet aurora. You cannot see that aurora on Saturn unless you have an ultraviolet detector, which is why these are Hubble images from Hubble up in space to be able to do the ultraviolet astronomy to see the aurora on Saturn. We can also look at galaxies in the ultraviolet. Again, we're getting to higher energy here. So instead of looking at that low dense, that cold gas, we'll be getting at the higher energy, the hotter stuff. And so this is the visible light image of a galaxy called M74. And in the ultraviolet, you only see the star-forming regions. Okay, you see the high energy regions, because it is, as I talked about, those hotter stars that actually emit in the ultraviolet. And those hot stars are the more massive stars. Those very massive stars only live short lives, so they don't get outside of their star-forming regions. So studying star-forming regions in galaxies, you can find them very easily just by looking in the ultraviolet. Moving up in energy scale, we go to X-rays, which from roughly 10 nanometers down to 1/100th of a nanometer. Again, about a factor of 1,000 in wavelength region. All right, and for our purposes, we think of X-rays as being these medical observations. And as you can see, that there is a fracture here in one of these bones. Now, are these bones emitting X-rays? No, the bones are not emitting X-rays. Rather, the X-rays are created by a machine that pass through the skin and the bones, right? The X-rays are actually absorbed by the bones, and what you're seeing the bones in shadow, because the bones actually are absorbing the X-rays, whereas the skin and soft tissue let the X-rays pass through. Right? So what you are seeing here is not an emission of X-rays, but rather an absorption of X-rays. So, knowing that, can anybody explain to me how Superman has X-ray vision? Because are his eyes X-ray detectors, or are they X-ray emitters? And if they're X-ray emitters, are the X-rays sort of somehow coming back to him so that he can detect them? It's never made any sense whatsoever. Okay. But astronomers truly do have X-ray vision, all right? And our favorite X-ray vision satellite is the Chandra X-ray Observatory. And the Chandra X-ray Observatory is on this really cool looping orbit around Earth. It's got this big, long elliptical orbit. All right? And observing X-rays is not like observing with visible light, because we usually bounce light off a mirror, right? Well, you take X-rays, it's going to go straight through the mirror. Okay? So you can't use a standard mirror to observe an X-rays. But you do use mirrors. And instead what you use are what we call grazing incidence mirrors. Okay? So the light comes in and it just deflects a little bit off of these mirrors. Okay? So you can see this is a concentric cone of mirrors that are graduated down to focus the X-rays onto the detector. Kind of cool, isn't that? All right? So instead of bouncing things off mirrors, you're just trying to give them this tiny little deflection. You're giving them a nudge, all right, to try and eventually focus them to focus X-rays. So I thought that was a kind of cool thing. So they have these basically these big concentric cones of mirrors that allow us to observe in X-rays. And we can look in X-rays at things like this. We can look at the sun. Okay, like we observed ultraviolet, which is where most of the activity is. There's still some even higher energy activity on the sun that shows up in X-rays. And this is from the Yoko satellite, which observed for several years. And the Yoko satellite also observed for over the course of a solar cycle. And so here you can see the high energy activity during a solar maximum, and then the low energy during a solar minimum. Our sun goes through these cycles of activity. All right, and when we look at visible light, we just see more sunspots or fewer sunspots, okay? Lots of sunspots and almost no sunspots, right? Here, it's much more apparent. You can see that's a seething cauldron of activity, and this is kind of boring. Okay, let's go check back next week. All right, so this was really nice in the 1990s to see a vivid illustration of the solar cycle observed in X-rays. We can also go back to that supernova remnant, Cassiopeia A, which I showed you in radio. But this time, let's take that visible light, which is just the shell at the edge, and let's take a look in X-rays. And in X-rays, you see all the heated gas interior to it. Because this is a star that has exploded its guts across space. Its stuff has been moving at tens of millions of miles an hour across space. It's heated up to millions of degrees. And in millions of degrees, you emit X-rays. Okay? So this is the gas that's interior. This shows you just the edge of the bubble. This shows you the gas in the interior of the bubble emitting X-rays. So supernova remnants are much more interesting to view in X-ray light. Another thing that shows up in X-ray light is the gas in clusters of galaxies. All right, so this is going to take a little bit of comprehension here. So we look at this image of a galaxy cluster. I forget which one this one is. I think this is one of the MAX clusters. All right, and you can see all these galaxies here. And if you look at those galaxies, right, and you say, okay, well, each galaxy has a certain amount of mass associated with it, and you can come up with a mass map, okay? And so we're going to color the mass in blue. So based upon all the galaxies out there, okay, that you can see and identify as part of this cluster, here is a rough mass map of that cluster based upon the light. All right? We can also look at this cluster in X-rays. And when you form a cluster of galaxies, you bring in not just the visible light of the galaxies, but all the associated gas associated with it. And you bring galaxy after galaxy swooshing together to make this really big cluster. That intra-cluster gas heats up. It heats up to hundreds of thousands and millions of degrees and actually glows in X-rays. So when you look at a cluster of galaxies like this and you look in X-rays, you see what we call here a red blob. All right? That is the gas between the galaxies, very low density gas, but has been heated up to hundreds of thousands and millions of degrees and glows in X-rays, which gives you another measure of the structure of the material in the galaxies and the extent of this cluster of galaxies. So if we put them all together, we've got the galaxy image in the yellowish stuff, we've got the blue for the mass, and we've got the red for the X-ray gas. All right? And it shows us that by looking in X-rays, we can discover the true extent of a cluster of galaxies, of all the stuff in the cluster of galaxies. It actually gives us another check on how we can compare the mass that is in visible light to the total mass that's in the entire cluster measured by the X-ray gas. All right, last wavelength region, the gamma rays. All right, wavelengths less than 1/100th of a nanometer. And we don't have a lot of everyday experience with gamma rays, but you do get them a little bit. Gamma rays can be produced by lightning strikes. All right, lightning strikes can produce just a little bit of gamma rays. Of course, where do we normally think of gamma rays? Besides the Incredible Hulk and, mutants like that, okay? We think of it with nuclear explosions, okay? Only in the highest energy events do we get gamma rays. All right? And so where would you get them in the universe? How would you look for them in the universe, okay? Well, of course, you have to go up into space. And the current gamma ray observatory is called Fermi. It used to be called GLAST, Gamma Ray Large Area Space Telescope, and now it's the Fermi Gamma Ray Space Telescope, and here is a drawing of it. And in this cube are lots of detectors for measuring the gamma ray radiation. Okay? And in particular, when you get up to these high energies, you're not measuring particularly the gamma rays themselves, you're measuring the gamma rays are absorbed and they create follow-on radiation, showers of radiation as they're absorbed, and you're actually detecting some of that showers of radiation, not necessarily the gamma rays themselves, but you can calibrate it really, really well to see it. So here is some of the results from Fermi. This is an all-sky image from Fermi, all right, before and after. and after when we see this giant splotch. Okay? This is a gamma ray burst. Okay? It is a single point of gamma rays emitted from somewhere in the universe. Secret. Astronomers didn't discover these. All right? Because gamma rays come from nuclear test explosions, all right? The Department of Defense put up gamma ray satellites, gamma ray detectors, to monitor whether or not there were nuclear explosions going around the world. And they saw bursts. And they saw another burst. And they saw approximately one burst every single day. How many nuclear bombs were there in the world to get an explosion every single day? Well, they quickly determined that no, they weren't coming from Earth. They were actually coming from space. And of course, this was classified, so they didn't bother telling astronomers. But we put up our own satellites and found it ourselves. So we've got these gamma ray bursts coming from somewhere. These are huge, incredible energetic events. All right? And there's not just one of them, okay? There are lots of them. Here are 2,000 observed by the Compton Gamma Ray Observatory with the BATSI experiment. All right? 2,000 of these all across the sky. And remember, when we're looking at this projection in the sky, the galaxy is right across the center. So you can see these gamma ray bursts are not associated with our galaxy. They're either really close to us in space, all right, around us within our small portion of the galaxy, therefore they can appear isotropic, or they're much further beyond our galaxy. And if they're further beyond our galaxy, they have to be incredible energies, okay? Because the further away they are, the more energetic they have to be in order for us to see them in gamma rays here. Well, it turns out they are actually at cosmological distances. All right? Here is a picture of a gamma ray burst in visible light. Can you see it? Yeah, I wouldn't know unless I put this arrow in. Okay? This is an object that produced a gamma ray burst. So after seeing a gamma ray burst in gamma rays, they put out the coordinates and you take images to try and see what you can find. Hubble has looked to see what it can find at the positions of these gamma ray bursts. And what does it find? It finds very distant galaxies. These gamma ray bursts are incredibly energetic events coming to us from cosmological distances. We're talking billions of light years, hundreds of millions to billions of light years away. Okay? All right? What we surmise them to be are something called not just a supernova, not a nova, not a supernova, but a hypernova. Okay? Which would be an incredible burst of energy, such that we can observe gamma rays from billions of light years away across in this. And that's why they are produced all the way across the sky. So it's an amazing and astounding idea that we can see these gamma rays from across the universe from these absolutely incredible explosions. And of course, that's not the only thing we see in gamma rays. Here is an all-sky map above 100 million electron volts, which is a really high energy. Let me just say that. And what we see a lot in that, here you can see the structure of our galaxy because we start seeing the X-ray binaries, we start seeing pulsars, basically black holes. All of those things that can produce really high energies are the only things that are going to be able to produce these gamma rays that we see with gamma ray telescopes. All right. So, we've covered the electromagnetic spectrum, all right? We've gone across all these wavelengths. Let's summarize in terms of what do we get out of it, okay? You've seen that we see lots of things in lots of different ideas of light. We have three great observatories currently operating. The Compton Gamma Ray Observatory isn't operating anymore. Hubble, which is mostly visible. Spitzer is infrared. Chandra is X-ray. We've done a variety of presentations where we take the same observations with these telescopes of the same object. I like to show this one here, which is a supernova remnant, supernova 1604, also called Kepler supernova, because here is where Hubble has the wimpiest of all the images. We're so used to Hubble having the most beautiful images. Well, when it comes to supernova remnants, at least this one here, even Spitzer in the infrared has more detail and more visual interest. And Chandra, of course, getting that hot X-ray gas inside the supernova remnant has the most interesting. Okay, so Hubble doesn't always have the most beautiful image. But even when Hubble does have a beautiful image, such as for the Crab supernova remnant, all right, then when we look in other wavelengths, we get a lot more information. Okay, in terms of from the radio, the various infrared bands from Spitzer, we've got the visible light here, we've got the ultraviolet in here, and down in the X-ray we can actually see the disk of material around the pulsar at the core of the Crab Nebula. Right? This is what astronomy has progressed to, being able to look in these various wavelengths of light and get different aspects of the same objects in these different wavelength regions. And I'm going to finish with my favorite object to do for this, which is, of course, the Whirlpool Galaxy. I've shown you the Hubble invisible, the Spitzer infrared. Here is the ultraviolet image. I believe that's the ultraviolet image from Galax. And here's the X-ray image from Chandra, where we're able to see different structures, understanding it together. And so this is a poster that we produced in the Office of Public Outreach, where we work through it to try and help express the idea that over the last century, we have gone from just visible light observations with the normal telescopes that you think about, adding in radio and infrared and ultraviolet, and across the entire electromagnetic spectrum. So astronomy has grown up to explore the entire spectrum, and there truly is more to the universe than meets the eye. Thank you for your attention. All right, so I filled you with all sorts of things all across the spectrum. Do we have any questions that I can answer? Yes, there.
I've never thought of this question until I've seen this presentation. For the visible spectrum, it's pretty obvious, but for all these other named spectrums, are there scientific properties that define the edges, or did Steve discover X-rays and said, I claim this set of spectrum for X-rays, and that's it?
Actually, Austin discovered X-rays, but...
yeah, Steve, that's his first name.
That's Steve? Oh, I didn't know it was Steve. Okay. Okay.
But what
generally, I would say that they're more defined by the detectors than they would be by the wavelengths. Okay, so a detector that can detect, wavelengths from here to here, well, that would define a region, right? So if X-rays, you have a detector that can detect the X-rays, that would be more. Because we often, if I go back to the Crab Nebula image, you can see we have near-infrared, mid-infrared, and far-infrared. We use slightly different type of detectors for each one of those regions, okay? We talk about millimeter wave and microwave, which are really the same thing. But, there's different ways that you use to detect them, okay? As you're working through them, yeah, the visible light, yeah, it's defined by what the human eye can see, but the other ones, they're more...
There's been the limitations of the detectors that kind of carved that out for that one spectrum, and then somebody gave it the name X-ray.
Sure, let's go that. The names for them, I really don't know the history of how they got named for that. But really, what you can do, I truly believe it's the detectors that sort of carved out the regions for that. Yes?
You showed a slide with a black hole and some radio waves emitting from it.
Yeah.
Black holes typically have such a strong gravitational pull that nothing escapes. How are the radio waves getting away?
Good question. Okay. So what's happening is it's not the black hole that's emitting. It's the material around the supermassive black hole. You've got this disk of material spinning around the supermassive black hole. You've got magnetic fields that are being spun up like this, and you've got material being flung off those magnetic fields. Okay? So it's not the emission isn't coming from the black hole itself, it's coming from the region around it. Okay? So, very good question. It's one of these things that's easy to gloss over when you know the answer. So, thank you for checking me on that. Yes?
Frank, you had a picture up there of a collection of galaxies, and then you did a picture of it in X-rays, and it was a red blob.
Yes.
And you used the term hundreds of thousands of degrees for all this gas.
Yes.
Can you quantify that a little bit, please?
The gas is at very low density.
Okay.
Right? but the temperature is basically a measurement of its motion in that, okay? So if we were 100,000 degrees at the density of Earth, it would be really, really hot, right? But at really, really low density, you're just measuring what the temperature of a gas is a statistical measure of how fast, on average, the molecules are moving. So you can have, 1 particle per cubic centimeter, or 1 particle per cubic mile, and if they're moving at the same speed, they have the same temperature. But the way you and I would experience temperature would be totally different for those. Okay?
Thank you.
Great. Yes?
Are all of the gamma bursts from long ago and far away?
If they're seen a billion light years away, they happened a billion years ago.
Have they stopped?
So if we ever see the gamma rays just stop, we go, oh, well, somebody flipped the switch, all the numbers turned off. I don't think that'll happen.
There aren't any young ones, though.
The gamma ray bursts that I know of are, hundreds of millions to billions of light years away. I'm not an expert on that, but I don't know of any that are that nearby. Okay, yeah.
That whirlpool galaxy in infrared was the center thing looked pretty much like red. But what's that satellite? What color is that? Brighter or dimmer?
Okay. So in the Spitzer view of the whirlpool galaxy, all right. So these blue here is actually going to be hotter in the infrared. Okay. A lot of times, what they will do is for the infrared, which doesn't have any colors, right? So they'll take the lower energy of infrared and map it to red, and the higher energy map it to blue. So just sort of corresponding to. And so these are actually, this is the satellite galaxy, okay? And what you're seeing there are the stars, okay? I believe what you are seeing there are the dwarf stars, the young, the low mass stars, which dominate the light from this dwarf galaxy, okay? Yes, right there.
It seems like James Webb is infrared.
James Webb is infrared, yes.
Why is that so important now, that wavelength?
Okay, so JWST will be able to look at, as I said, the star formation, look in to see the formation of stars and planets, okay? Because you'll be looking through the dense gas that Hubble, for example, can't look through. The other thing that why infrared is really important is to look at these very distant regions of the universe. Because as the universe expands, light waves that are traveling across the universe get stretched along with the expansion of the universe. So light that started out in visible light gets stretched and becomes infrared by the time we observe it.
The Doppler.
Okay? No, it's that's cosmological redshift. Okay? This is the expansion of light, the stretching of light due to the expansion of the universe. All right? And so if we want to observe the distant universe, even if we want to see ultraviolet radiation from the very distant universe, that light has been stretched now to the infrared, so we have to use an infrared telescope to see it. There are some things Hubble can't observe simply because their light has been stretched beyond Hubble's observing wavelengths. That's another reason why JWST will be so important. Okay, in the back there.
Hey, I got a question. If you're way out in space and you look back at our galaxy and you want to look into our solar system, which type of telescope would you look through? Would it be infrared? Would it be visible?
So how far out in space am I? Am I the Andromeda galaxy, which is 2 million light years away?
Okay, just...
Or am I the Virgo cluster, which is 60 million light years away?
Just give 2 examples of the two
Okay, so if we wanted to see the emission from our sun, okay, and we were, at the Andromeda galaxy, 2.5 million light years away, we would use an optical telescope because that's what the wavelength that our sun emits at, right? And so the Earth, which only shines by reflected light, which has a little bit of infrared emission, but mostly it's going to shine by reflected light. If we wanted to see that, we would try and see the light reflecting off Earth from our sun, so we'd want to use a visible telescope. But if you get really far away and the cosmological expansion stretches that with those wavelengths, then they would go towards the infrared, right? Okay? Our solar system doesn't have a lot of dust and gas in it, like the HL Tauri system that I showed you from that ALMA observation. That's a system still in formation. there's still lots of dust and gas and cold and stuff floating around in that system. So that's why using the millimeter array is better. But since ours is a system that's relatively devoid of that stuff, you'd want to use visible or infrared. Okay, great.
Most of what you've been talking about are objects that are emitting light at these various wavelengths.
Yes.
Now, what about observing objects that are reflecting light at these various wavelengths? And does observing at some of these shorter wavelengths give you more detail than at the longer wavelengths?
Well, let's see. So first of all, there are only a few cases where we observe reflected light and get a lot of it. Okay, I showed you the reflection nebulae around the Pleiades, etc. Around supermassive black holes, where there's a light, when there's energy being emitted from those, that hits a disk of material. That disk ends up re-radiating that, can absorb it and re-radiate it. Some of that can also be reflected in there. But not a ton of cases where there's a lot of reflected light to observe.
You see my point that with the shorter wavelengths, you would be able to see more detail than with a longer wavelength. Is
Right.
that?
So this is another thing to recognize, especially in terms of the James Webb Space Telescope. The James Webb Space Telescope being 6.5 meters, Hubble is only 2.5 meters, but the resolution is roughly the same because this is the JWST is at infrared wavelength, which is a longer wavelength. So the shorter wavelengths do give you a higher resolution on things like that. However, the fact that we can get a radio telescope to stretch across miles and miles and miles actually gives radio the highest resolution. All right?
And also about the
Because it's the size of the telescope versus the size of the wavelength you're looking at, right? That gives you your resolution. So if you have, gamma rays are hard to pinpoint, etc. Because they actually get scattered. If you're observing them, the way we detect them doesn't pinpoint them exactly, right? Because we see that there's a shower coming off of them, it doesn't give you that hyperfine resolution the way a mirror observation would. Okay, so but radio, by having these very, very large arrays, all right, which simulate a telescope having an aperture that big, compared to the wavelength, can actually give you extremely high resolution imagery. So when we say Hubble is the highest resolution, right, it's the highest resolution visible light telescope out there. It's not the highest resolution telescope at all up there. You can see that the ALMA array has much higher resolution. Looking in the
Do you get more information from the VLA with the fact that it's moving around as the Earth rotates and as the Earth moves around the sun? Does that?
Not really.
No,
you can't. You have to be taking the observation simultaneously. You can't take an observation in January and correlate it with an observation in June, right? That would be really cool, wouldn't that? Right? But no, you can't do that. The current techniques are simultaneous observations by two telescopes at the same time, so the wave front can be correlated between the two of them. All right. Any other questions? Yes, down front.
We're doing spectroscopy with visible light.
Yes.
Is it possible to utilize for a very, very distant object spectroscopy, utilizing, let's say, for the sake of argument, the different frequencies?
We use spectroscopy is not limited to just visible light. Okay, we can take infrared spectra, we can take ultraviolet spectra. Matter of fact, when we're looking for when we're looking at the atmospheres of extrasolar planets, right? We want to take a spectra in infrared to try and identify the molecules in the atmosphere of an extrasolar planet. So to see the details, the juicy details that we want, they're actually in the infrared. Okay, so we can do spectra across the spectrum and the various things. A lot of them in some of the wave bands, it's just you take a detection here, a detection here, a detection here, and you sort of synthesize the spectrum through it, as opposed to taking many, many, many wavelengths as we do with visible light. Okay? All right.
We know that visible light is affected by gravity. I assume all energy is. Now, would one...
Let me just say right there. Visible light is no different from infrared light, or no different from ultraviolet light, so gravity affects visible light, it affects other light as well.
Right.
So same thing, go ahead.
So would one end of the spectrum be heavier than the other? In other words, would it be more bent or less?
If it affects it, if the effect that you're talking about is dependent upon energy, yes.
Right.
All right, so the bending of light, all right, high energy wavelengths are refracted more than low energy wavelengths. When you create a spectrum with a prism, all right, the red light is refracted less than the violet light. Okay, so there's one example of how things differ by wavelength. All right, one last. Somebody back. You guys come up with all sorts of questions here.
Following up on that question, in visible light, you have the gravitational lenses, those like the blue arcs. Do you get images like that in the other wavelengths?
So So the question is, do we get gravitational lensing in other wavelengths? The answer would be yes. We should. Theoretically, there's no reason we shouldn't get gravitational lensing in other wavelengths. I do not know that I've ever seen a picture of it. Because you need really high resolution. I mean, Hubble has done amazing things with gravitational lensing with visible light, because light is light, okay? And it's going to get affected by the gravity, even if it's at a different wavelength. Yes, you should get gravitational lensing. I know we get gravitational lensing of infrared. Okay, even Hubble's observations in the infrared sees gravitational lensing in the infrared, but I can't say I've seen it in other wavelengths beyond visible and infrared.
Is light a wave or a particle?
Yes.
Okay.
Just an observation. Thank you for more accurately locating the APL in Columbia as opposed to Laurel, which is not near.
Well, I've been in APL, and it's off one of the exits that's right next to Columbia. So the press all call it Laurel, Maryland.
Yeah, because of a gerrymandered zip code, it's actually in the Laurel zip code, but it's
in the Laurel zip code.
yeah, but that's a
okay. All right, ladies and gentlemen, we will see you in October. Thank you very much. If you would like to go to the observatory, we have our observatory person here. Yes, over here, this gentleman in the brown shirt. If you would like to go to the Maryland Space Grant Observatory, come down here and talk to him. He'll take you across the street for the observing tonight. Yes. What aspect of that is? Yeah, okay. So we had Mark Kaminkowski speak on that. The B-mode polarization, trying to see if gravitational waves would affect it. So what is really great about the cosmic ray background is that we've gotten such good observations of it. We can now look for tiny variations in the way. And so one of the ways we can look at it is look for polarization.